Good evening, everyone. I'm Dr. Andrew Hines from the School of Computer Science. On behalf of my colleagues in the school, the UCD College of Science, and across the university, I would like to warmly welcome you to this evening's presentation of UCD's highest honor, the Ulysses Medal, to Professor Geoffrey Hinton. A few housekeeping points. Please make sure that your mobile phone is switched off for the duration of our event, and take note of the nearest fire exit in the event of an emergency. This evening's formal proceedings will be presided over by Professor Orla, President of UCD. This is a very special occasion for the university and a wonderful reason to bring faculty, staff, students, and alumni together. Before we commence, I will explain the procedure which we will follow. Firstly, I will read a citation for Professor Hinton. UCD President Orla will present the Ulysses Medal here on stage. I will ask Professor Hinton to respond to the citation. And bringing formalities to a close, I will ask Professor Feely to address you before I'm joined on stage by Professor Kate Robson-Brown, UCD Vice President for Research, Impact and Innovation, for a fireside chat. I'm delighted that Professor Hinton has agreed to take questions from the audience. President, Registrar, distinguished guests, colleagues, Ayina Usha. On behalf of the President, Neil Hurley, our Head of School of Computer Science, and all of my colleagues here at the university, it's my pleasure to introduce Geoffrey Everest Hinton, as we recognize this evening his contributions to the field of computer science, both in computational and engineering breakthroughs that have made deep neural networks a critical component of computing. The UCD Ulysses Medal is the highest honor that the University College Dublin can bestow. It was inaugurated in 2005 and named after UCD alumnus James Joyce. It is awarded to individuals who have made an outstanding global contribution. As all academics will probably be familiar with, there's a challenge to creating a concise yet comprehensive review, and Geoffrey Hinton's career is particularly hard to distill. He spent decades understanding the human brain to draw inspiration to create better computer learning models. Now that these technologies are integrated into products and services that we use every day, the moniker of Godfather of AI is not an exaggeration. For the last year, he has been sharing his knowledge with a wider public audience than at any time during his busy career. He is raising awareness and concerns about how humanity will use and develop artificial intelligence. As to whether this could damage his lifetime of accumulated respect, he has remarked, "I don't really care about my legacy. The best thing you can do with a good reputation is squander it." From my perspective, these are the words of someone who we should carefully listen to. He received his BA in experimental psychology from Cambridge in 1970 and his PhD in artificial intelligence from Edinburgh in 1978. He's an emeritus distinguished professor at the University of Toronto and is a fellow of the Royal Society of Canada, the Association of the Advancement of Artificial Intelligence, and an ACM fellow. He was awarded the Turing Award, which is computer science's equivalent to the Nobel Prize, in 2018, along with Jan LeCun and Joshua Benigo. After completing his PhD, he spent time at the University of Sussex, the University of California, San Diego, and Carnegie Mellon University, before moving to Canada, to the University of Toronto in 1987. In 1988, he returned to England as founding director of the Gatsby Computational Neuroscience Unit at University College London, before returning again to Toronto. He spent 10 years working part-time with Google as a distinguished scientist before retiring in 2023 to allow him to talk more freely about AI without any potential conflict of interest with Google's shareholders. So he could, in his words, talk about the dangers of AI without considering how this impacts Google, because Google has acted very responsibly. Having mentored over 30 doctoral students, Those who have worked in his lab as graduate students and researchers have gone on to mentor future generations of researchers, whether in academia or in industry, such as Jan LeCun in Meta and Ilya Sutskever in OpenAI. Professor Hinton comes from a family of with a distinguished academic legacy of committed researchers and educators. Mary Everest Boole, his great-great-grandmother, was a self-taught mathematician and author, and sought to make mathematics more engaging for children, writing a book, Philosophy and Fun of Algebra. And she was married to George Boole, who was the first professor of mathematics at Queen's College Cork, now UCC, who developed Boolean algebra, the logic that underpins modern computer science. His early work explored how artificial neural networks had the capability to learn complex representations. In 1986, with Rummel, Hart, and Williams, he published on the concept of backpropagation to help networks learn. He developed architectures called Boltzmann machines that became an important component of deep learning architectures. In the 2000s, a number of things converged. Compute power increased, particularly with GPUs, and also large data sets to train models for tasks such as speech recognition and image classification. I remember attending a special session at a conference in Vancouver in 2013, and the main questions were not about the theory, but rather about the implementation. How can we do this too? How can we get the code to run on these GPUs? The engineering contribution was almost as important as the science. In his 2012 paper, ImageNet Classification with Deep Convolution Neural Networks, it has more than 120,000 citations, according to Google Scholar. It demonstrated the power of CNNs for image recognition. Since then, he's continued to contribute with work on capsule networks, contrastive learning, and new hardware solutions for AI. Geoffrey Hinton's impact on the field of AI is undeniable. Deep learning has revolutionized AI across computer vision, natural language processing, speech recognition, finance, medicine, many areas. He is a very worthy recipient of UCD's highest honor. And now I'd invite the President, Orla to present the Ulysses Medal to Professor Hinton.
Thank you very much for that very generous citation. I want to sort of make one particular point about it, which is that my success has been largely due to being able to recruit really brilliant graduate students. So one should never forget that in this field, it's the graduate students who do the work. I can't resist an opportunity to lecture people about things, and there's a lot of people who don't actually know how AI works. So my apologies to computer science students and people who already know how AI works. I'm going to give a sort of very basic talk for about 20 minutes about how AI actually works, designed for people who don't like equations and don't know what on earth these big chatbots are doing or how they do it. So since the middle of the last century, there were two paradigms for intelligence. There was the logic-inspired approach, where the idea was the essence of intelligence is reasoning. That's what makes us special. And that's done by using symbolic rules to manipulate symbolic expressions. And things like learning can wait till later. What we really have to do is understand how knowledge is represented, what kind of logical type language is represented in. And then there's a biologically inspired approach, which is completely different. It said the essence of intelligence is learning. Logic and stuff comes much later. And you learn the strengths of the connections in a neural network. And things like reasoning we'll deal with later. To begin with, we have to understand how you do learning for things like controlling your body or recognizing objects. And so what is a neural network? I'm going to give you a kind of caricature of a neural network. You have some input neurons, which might be the intensities of the pixels of an image. So that's the data. And then you have layers of intermediate neurons, and they're going to learn to extract features from the image. And then you have output neurons that might say what it is an image of. There might be one for cat and one for dog, for example. And so what you like to do is input a picture of a cat, and the cat neuron turns on at the output. And those little colored dots on the connections are the connection strengths. And what you're going to do is learn the connection strengths so that the right thing happens. So there's a simple way of doing that learning that everybody understands. You start with some random connection strengths, and then you take one of the connections, and you see if, when you change that connection a little bit, let's say you increase it a little bit, the network gets better. Of course, deciding whether it gets better, you have to run quite a few examples through it and see if it produces better answers. So initially, it might have said the probability that this cat image is a cat is 50%. And when you change this weight, it might say it's 51%. OK, so that was good, so you change the weight like that. And then you take another weight and you try that. And you keep doing that. And if you do that long enough, you'll get a network that when you show it a cat says it's very probably a cat, and when you show it a dog says it's a dog. But it's very, very slow, because for each connection, you have to try many examples. And you have to update each connection many times. Now, it turns out you can achieve the same thing in a much more efficient way by using an algorithm called backpropagation, where you take an image of something, you put it forwards through the net to get a response, and let's suppose it says 50% it's a cat. So you've got an error, because you'd like it to say 100% it's a cat. So you send a signal back through the network, back through the same connections, which is conveying the error. And basically, you can compute, rather than measure, how changing each weight would improve the network. So for each of those weights, you can figure out, if I raise this weight a bit, will it make things better, or will it make things better if I lower this weight a bit? But you can do it for all the weights in parallel. So if you have 1 billion weights, that goes 1 billion times as fast. And that's how neural networks work. The math of how you compute how to change each weight by backpropagating the error is just some relatively simple calculus. The point is, it really works. You can learn things that way. So, for example, for many years, computer scientists, computer vision people, would have liked to take an image like that one and produce as output a caption that says what's in the image. And they couldn't do it. They couldn't even get close. And now neural networks can do that. And they're trained with this backpropagation algorithm. And the backpropagation learns a hierarchy of features to extract from the image that do enable you to see what's in the image. And in 2012, Alex Krzyzewski and Ilis Szyutskova, with a little bit of help from me, developed a network that was way better than existing computer vision systems. And something happened that's very rare in science, which is the leading computer vision experts, who'd always said neural nets will never be able to do this, said, wow, it really works. And they changed what they did and started using neural nets. That's not how scientists normally behave. And it's certainly not how they behave in linguistics. So that brings us to language. Many people in the symbolic AI community said, you'll never be able to deal with language by using hierarchies of feature detectors. It just won't work. You can see a quote on my webpage saying exactly that. And I couldn't resist it, so I got GPT-4 to explain in detail what was wrong with the quote. So we now have GPT-4 explaining to a linguist why what they said is wrong about what neural networks can and can't do. Linguists were misled for several generations by someone called Chomsky, who actually also got this prestigious medal. So it doesn't last. He had a crazy theory that language is not learned. And he managed to convince lots of people of that. And on the face of it, it's just nuts. Language is obviously learned. And now these big neural networks learn language, and they didn't need any innate structure. They just started from random weights and a lot of data. And Chomsky is still saying, but this isn't really language. This doesn't count. It's not right. And yeah. And lots of statisticians and cognitive scientists also said, you'll never learn language in a big net like this. So Chomsky never really had a theory of meaning. It was all about syntax. And if you think about meaning, there's two very different theories of meaning. There's the structuralist theory that the symbolic AI people believed in, and most linguists believe in, which is the meaning of a word comes from its relationships to other words. So if you want to capture the meaning of a word, you need to make a relational graph that has links to other words, and maybe labels on the link saying how it's related to those other words. That will be a semantic net. And that's what you need to capture meaning. And then there's a very different theory which comes from psychology in the 1930s, which is the meaning of a word is a big set of features. And words that have similar meanings have similar sets of features. And those two theories look totally different. But actually, you can unify those two theories. And I think the first model to do that was a model I produced in 1985, which was a tiny language model. And it had a lot in common with the big language models now. It learned by trying to predict the next word, and it learned features for each word and interactions between those features so that you could predict the features of the next word. And the important thing is, all of the knowledge was in what features to assign to a word and how these features of different words should interact. It didn't store any sentences, but it could reconstruct sentences. It could generate sentences by repeatedly predicting the next word. And that's how these big language models work. They don't actually store any text. They learn to extract from text features to assign to words and interactions between those features so that you can predict the features of the next word. And this tiny language model wasn't designed to help with engineering. This tiny language model was designed to explain how people can get meaning out of language. So it was actually a model of people. And if you see people telling you, these models aren't like us, they work completely differently from us, ask them, well, how do we work? And if they're linguists, they'll tell you we have symbolic rules and rules for manipulating symbolic expressions. But actually, the people who say they're different from us don't actually have a model of how we work, so I don't know how they know they're different. Whereas the neural net people do have a model of how we work, and it's just like this. Not exactly like this. So I'm going to go through a small model in detail, because I always believe that understanding a small concrete thing is much better than waffly abstractions. Waffly abstractions are great, but to really understand things, you want a little concrete example. So here's two family trees. There's some English people and there's some Italian people. And this is 1950s. It's very, very simple families. No divorce, no adoption, no same-sex marriage. The whole thing is very, very conventional. And you may notice that the trees are kind of analogous to one another. They have the same structure. And we're going to turn those relational trees into a bunch of triples. So from those relational trees, we can write down the information by having some relational terms like son, daughter, nephew, niece, mother, and so on. And then we can make triples like Colin has father James, or Colin has mother Victoria, or James has wife Victoria. Now, from Colin has mother Victoria, and from Colin has father James and Colin has mother Victoria, we can infer James has wife Victoria. And so the symbolic people thought you had representations of those symbolic strings in your head, and you had a rule in your head that allowed you to derive new symbolic strings from the old ones. And the rule might look something like this. If X has mother Y and Y has husband Z, then X has father Z. And that's how they thought it all worked. And what I did was made a neural network where you can learn that knowledge by just tinkering with the weights of the network, but it doesn't have any strings stored inside it. No symbolic expression stored inside the network. Inside, it's all features and interactions of features. And the thing about doing it in a neural network is, for discrete rules, you might be able to do it symbolically, but most of what we know isn't exactly right. You have to allow for a lot of exceptions. And as soon as you get exceptions to rules, you're much better off finding these rules by using a big neural net. So the neural net I used looked like this. You had two inputs. One was a symbol, just a discrete symbol, representing the name of a person. And the other was a discrete symbol, the name of a relationship. And the output we wanted was the name of the person to whom they were related like that. So that was what the training data was like. And what the neural net learns to do is convert the name of a person into a bunch of features that capture the essence of that person. The essence, insofar as these family trees are concerned. And once it's done that for the person and the relationship, it makes those sets of features interact in the middle there so as to predict the features of the output person and from the features of the output person, it predicts who the output person is. And that worked pretty well. It could learn, and it could not only reproduce the facts it was given, that is, the information in the learned weights was enough so that if you gave it a training example, it would get the right answer. But it could also generalize. You could give it examples it had never seen before, people it had seen before, and relationships it had seen before, but combinations it hadn't seen before, and it could get the right answer. And the question was, how did it do that? Well, it learned what we would think of as natural features. So for a person, it learned features like, what nationality are they? Because if you know the input person's English, you know the answer's English. If the input person is Italian, the answer's Italian. Like I said, they were very simple families. It was a tiny net. It only had 6 neurons in the bottleneck. One would represent nationality. Another would represent what generation the person was. Another would represent what branch of the family tree they were in. And the generation feature would have 3 values, because there were 3 generations there. It could be the lowest or the middle or the top generation. And that generation feature is only useful if, for the relationships, you learn features like, this relationship requires the output person to be 1 generation up from the input person. So a relationship like uncle would be like that. And then if it knows the generation of the input person, and it knows the relationship what's 1 generation up, it can predict the generation of the output person, and that will help it get the right person. So that's how it worked, and it had actually discovered the symbolic rules that symbolic people believed in. So none of the symbolic people complained this wasn't actually learning. They said, okay, it learns, but it's a stupid way to learn it. If you look at the large language models now, they can be viewed, well, I view them, of course, as descendants of this little model, and they're just this little model massively scaled up and made massively more complicated. So they have many more words. They work for natural language, not just these toy examples. They use many more layers of neurons, because you can't just go from a symbol to the meaning. You might have a symbol like May, and May could mean a month, or it could mean a modal, or it could be a woman's name. So you have to use context to disambiguate it. So you go up through layers disambiguating things. So they've got more layers. And the interactions between the features of different words are much more complicated. But essentially, it's in the same class of models. And when they learn, they store all the information in the weights of the interactions between features. Now, linguists say they're just glorified autocomplete, and they're just using statistical tricks, they're just pastiching together text. But remember, they don't store any text. And the autocomplete objection is crazy, because what they're appealing to is the idea of an old-fashioned autocomplete. Old-fashioned autocompletes would store strings of words, so they store fish and chips. That's a frequent string. So that if you store fish and, you then say the next word is likely to be chips, because that's a very frequent string. Autocomplete in these systems doesn't work like that at all. It converts the words into features and uses interactions between features to make the prediction. So the way LLMs work and the way we work is we see a lot of text, or we hear a lot of strings of words. We learn features for the words. We learn interactions between those features. And that is what understanding is. And these models are doing understanding in just the same way we are. And then another argument that linguists give you is these things hallucinate, so they don't really understand what they're saying. Actually, it shouldn't be called hallucination for a language model. It should be called confabulation. And that's been studied in psychology since the 1930s, and people do it all the time. So the fact that they confabulate actually makes them much more like us. And most people think a memory is like a kind of file that you put somewhere and then you go and retrieve later, like in a computer. It's not like that at all in a person. Memories are always reconstructed. If you're remembering something that happened recently, you'll reconstruct it fairly accurately. If you're remembering something a long time ago, you'll often get all the details wrong and won't realize it, and you'll be confident about them. There's a wonderful example of that, which is John Dean's memory. So at Watergate, John Dean testified under oath about what happened in various meetings in the White House, and he was wrong about all the details. He said Haldeman said this. Well, no, it was Ehrlichman said that, and Haldeman wasn't even in that meeting. And What's clear about his testimony is he was trying to tell the truth. He conveyed the gist of what went on when they tried to cover up Watergate. But all the details he purported to remember were wrong. Not all of them, but a lot of them. And Ulrich Neisser had a lovely paper showing that. And it's a lovely example of how things John Dean thought he could remember, when you listen to the tapes, he was just wrong. But he had the essence of it. Now, at present, chatbots are worse than us at confabulating. They confabulate more often than people, and they don't know they're doing it. They're getting better all the time. And I think in not very long, chatbots won't be much worse than us at confabulating. But the fact that they confabulate doesn't show they're not understanding or they're different from us. It shows they're very like us. And so that concludes my attempt to show you that these big chatbots are very like us. They're not like normal computer software. They're much more like people. And that leads to a whole bunch of AI risks, which I decided not to talk about. They're in this paper on archive, but I suspect some of you will want to ask questions about the AI risks. So I'm now done.
Thank you, Geoffrey, for your very thought-provoking speech and very accessible introduction to AI for everybody here. I think it'll be more memorable than John Dean's was for everybody. Now I'd like to invite the UCD President, Professor Orla to address.
Thank you, Geoffrey, for those very clear and interesting words. And thank you, Andrew, for your nomination of Geoffrey for the Ulysses Medal and also for delivering the citation. As Andrew mentioned, we'll shortly hear again from Andrew and Geoffrey, along with UCD Vice President for Research, Innovation and Impact, Professor Kate Robson-Brown, in a fireside chat where you'll get to ask all the questions that you presumably have stored up at this stage. I'll be brief but I do want to highlight some aspects of Geoffrey Hinton's work and background that for me make this award particularly fitting. The first of these speaks to the conduct of research that changes the world. When I was a graduate student in Berkeley in the 1980s, I encountered what was then the second major wave of research into artificial neural networks, with Geoffrey Hinton, one of the leaders. That meticulous, steady research endeavour continued over decades, bringing about change, first gradually and then very suddenly, when the technological capability had developed to the point where it could deliver on the power long anticipated in the algorithms. Geoffrey has spoken of the difficulty of maintaining a very high-level research career over that long time, describing in particular the challenges that he faced when he was a widower with young children. He has highlighted the importance of mentorship, and we are very grateful that he took the time this afternoon to do an Ask Me Anything session with our students. His research has spanned industry and academia and has brought together domains such as psychology and physiology, as well as engineering and computer science. He has also, crucially and famously, spoken very publicly about the societal implications of artificial intelligence. For us as a research community in University College Dublin, it is important to hear and to hold these messages of the importance of fundamental understanding, of vision and perseverance, of mentorship, collaboration, and open questioning. The second aspect that I would like to highlight is the link to Ireland. Andrew spoke of Geoffrey's family links to George Boole and Mary Everest Boole and their multi-talented descendants, of whom we in Ireland, and particularly our friends in Cork, are very proud. In today's Ireland, we have a country that has worked very hard to develop an enviable presence on the global technology landscape, including the ability, not to be taken for granted, to keep up with successive waves of technological progress. What does the prospect of widespread adoption of artificial intelligence mean for the technology sector and other sectors in Ireland? Where will the opportunities reside and the challenges? What are the demands on computing and on other infrastructures and on the talent pipeline? And for us in UCD, a university that has more than any other supported and enabled national progress, how do we address the opportunities and challenges of artificial intelligence in our teaching and learning and in our research and innovation? We have outstanding work already underway in this area, not only from Andrew and his colleagues in computer science, but across the university, as seen, for example, by the award-winning work of Professor Patricia Maguire and her colleagues on the application of AI in the treatment of preeclampsia. As we embark on the process of forming our next university strategy over the coming months, the question of how artificial intelligence will figure in that strategy is a very important one for us. And the third aspect that makes this award so fitting relates to where the world is currently poised in relation to artificial intelligence. James Joyce's novel Ulysses, after which this award is named, is one of the great examples of human creative intelligence. We are now challenged to reflect on our understanding of intelligence, of creativity, and even of what it means to be human, as we seek to chart a course through ever greater adoption of artificial intelligence. For some, this prospect is exhilarating. For others, it may be daunting or even dystopian. Either way, we cannot chart our course by wishing away the power of technological disruption or by succumbing to that power without challenge. We cannot, at this point, foresee the full impact, the limitations, the applications, and the implications of artificial intelligence as it develops over the coming years and decades. What we do know is that we need to understand, in as much as we can, the capabilities and the limits of this technology, to bring all disciplines and viewpoints into the conversation so that we can apply artificial intelligence for the good of humanity. In this, it is enormously important that we hear the voice of those such as Geoffrey Hinton, who have done so much to advance this technology and to inform public debate about its safe adoption. For all of these reasons, it is a great honour to have Geoffrey with us today, to celebrate his very distinguished career and to listen to his words. Thank you all for joining us tonight to be part of this conversation.
Thank you, Professor Feely. I would now like to invite Professor Kate Robson-Brown, UCD Vice President for Research, Impact and Innovation, to join us on stage for a fireside chat.
Thank you very much, and thank you, Geoffrey, for such a wonderful talk. I could see when I walked in that we have here a pretty diverse audience, and I hope you can see that that's a reflection of the warmth with which we want to welcome you here at UCD. I can see many younger and early career researchers in the audience as well, and I know you took time this afternoon to talk to a range of our students. So perhaps I thought it'd be nice to start there and think about what influence your own learning, maybe at school and college, has had on your later career. What is the thing that you look back on and say, that was really important to me, that's where I started?
I guess there's several things. One thing was doing physics. Physics gave me an idea of what it means to explain something. And when I did psychology, after having done physics, I didn't feel it was really explaining what was going on. I felt you really need to get at the real mechanisms. So that was important. Another thing was when I was a teenager, a friend of mine at school told me about relays and about how you could get one current to switch on another current. And so I actually spent quite a lot of time cutting the heads off 6-inch nails and winding copper wire around them, and then taking an old-fashioned razor blade and splitting it in two so that you had a flexible piece of metal, and putting a piece of copper wire around the end of the razor blade and a piece of copper wire across where the head of the 6-inch nail had been, And then when you put the current in, you make a connection. And that way you can make a little relay. And then I would wire up these relays in different ways and discover you could make things like oscillators. That was a lot of fun.
So what age are you at this point?
I'm probably about 15 then. I guess I could have just gone out and bought some relays. But
Where's the fun in that?
it was more fun making them. Yeah, I also think coming from a family where science was highly valued was important.
Another thing that strikes me, kind of thinking about your own career journey, is the fact that your research and your interest sometimes has sat in between the traditional silos of disciplines. So do you think that's a fair statement?
Yes, when I was at high school, I got very interested in how the brain works, because I had a brilliant friend there who was much smarter than me, who told me the brain stores memories like a hologram, and that got me interested in it. So he was a big influence on me. That was another big influence.
Yeah, interesting. And if you were looking back at your career, what aspects of it are you most proud of? And I'm not necessarily just thinking about your discoveries, but maybe other aspects of your career as well, the people that you've worked with, the teams that you've built.
I guess I'm proud of the fact that I stuck with neural networks even when people said they were rubbish, which was for about the first 40 years. But the intellectual achievement I'm most proud of is Boltzmann machines, which were an alternative to backpropagation. And they're probably wrong. They're not how the brain works, and they don't work as well as backpropagation. But they're such a beautiful theory that I'm very proud of it, even though it failed.
And in terms of advice for early stage career researchers working in academia now, what would you say to people who go, well, there's no compute power available to academics? How did the early stage researchers contribute now?
Yeah, I don't really know the answer to the compute power, except that try and persuade your government to provide more compute power. I think there's still lots of research to be done other than building these massive models. And one piece of advice I give to researchers is trust your intuitions. So basically a lot of good research comes from having a sort of vague intuition that there's something wrong with the way people are doing something. There's something just not quite right about it, and then pursuing that. So an analogy I like to use is when you read a detective story, often sort of in the first chapter, someone does something, and when you read it, it's just slightly off. It's slightly weird they did that. And it turns out later that's the key to the whole story. But you typically just read through it and don't notice it. You just feel slightly weird. A lot of science, I think, is like that. And if you have an intuition that people are doing things wrong in some funny way, work on that and don't give up on it until you know why that intuition is no good. And if it takes you 20 years to discover why that intuition is no good, then so be it. But either you have good intuitions or you don't. If you have good intuitions, you should trust them. And if you don't have good intuitions, it doesn't really matter what you do. So you might as well trust them.
There's a lot of early career researchers here, but there's also a wide cross-section of Irish society here as well. So a question more to do with the AI policy. What can academia and government and industry and philanthropists, what can they be doing together to change the long-term direction of AI to be more fair, safe, regulatable, in the interests of humanity rather than in the interests of big company shareholders?
So I think one thing governments can do is try and keep AI research going on in universities and cutting-edge AI research. And the way to do that is to provide a lot of money for compute. So Canada yesterday announced they're providing $2.4 billion for AI, and $2 billion of that is just for compute, so that Canadian startup companies and Canadian academic researchers can get significant amounts of compute. That's the kind of investment that's needed. And Ireland needs to maybe it's a smaller country, so it can't invest that much maybe, but maybe in conjunction with the European Union, it could be part of something in Europe that does invest significant amounts of money. So the European Union invested $1 billion in a crazy brain project that didn't produce anything. They'd be much better off investing like $5 billion in compute for AI, so that people in universities and small startups can compete with the big companies. That's one thing we can do. The other thing government can do is force the big companies to do more research than they're doing on safety. So I guess my political belief is that I'm really a socialist at heart, but capitalism has worked pretty well for some things. And it seems to me what you need is, you need the kind of creativity of small startups trying to get rich, but you need to have that in a strong regulatory environment. So the role of government is to organize things so that if everybody does what's in their own self-interest, it works for everybody. And the idea that the government should stay out of it, that's crazy, because then if everybody does what's in their own self-interest, you just get some very rich people and everybody else very poor. I think government should be very interventionist, and it should be trying to create a reward landscape that channels people into doing things that will be useful for society. So I think there's a lot government should be doing, and one thing in particular is insisting on more research on safety.
We can stay with that issue of safety, I think, at the moment. And I mean, particularly in terms of large language models like GPT-4 and others, which have got very wide adoption and are very much in the public discourse. Can you tell us something kind of specific about the concerns you have about misuse, and what we might do both in the short and the long term to mitigate against the risks?
Yes, so there's many different kinds of misuse of risk, and they all have different solutions, and there's different timescales. So the most urgent one at present, well, there's discrimination bias, which is going on already. They are, possibly because I'm an old white male, they're something I'm not that concerned about. And the reason is, if you replace an existing system with an AI system, you can make the AI system a bit less biased than the existing system. You shouldn't try and make it unbiased, that's just going to be hopeless. Just make it significantly less biased than what it replaces. So if you've got training data which involves old white men deciding whether to give mortgages to young black women, you know it's going to be very biased. The existing system is like that. Your training data is like that, but you can do things to make the final system less biased. You'll never make it unbiased. So I think bias, actually AI systems can make things a lot less biased than they currently are, even though they're not unbiased. The thing I'm most worried about at present is corrupting elections with fake videos, and we're going to see a lot of that this year. And obviously the solution to that, although it's difficult technically, is to mark all those videos as fake. Insist that AI-generated stuff be marked somehow as AI-generated. It's very hard to do technically. But I think in the States, for example, they're not going to even try to do that because there's no way the Republicans would vote for that. They're relying on telling lies.
Elsewhere,
that wasn't political, that was just fact.
You've also raised concerns about the potential for AI to create its own goals and potentially expose us to what might be described as an existential threat.
Yes.
So can you give us some examples of what concrete safeguards or ethical frameworks you believe are crucial to implement during this period of AI development that we're living through?
So, yeah, the existential threat is longer term. My guess is we'll get things smarter than us with a probability of about 0.5 in between 5 and 20 years from now. It may be longer, it may be shorter, but unlikely, I think. But there's quite a good chance that in that period we'll get things smarter than us. And if we do, there's quite a good chance they will take over. And we should clearly be thinking about how we prevent that. I mean, there is an issue about whether we're being, whether humanist is a racist word, whether they should have rights too. But we're people, and we care about people. And I think we should do our best to keep people around. I don't know if we can do it, though. But certainly one thing we should do is, as we make things more intelligent, as the big companies edge towards superintelligence, they can actually do experiments on how these things might get out of control before they're smarter than us. And anybody who's written a computer program knows that you write the computer program and then it doesn't work, and then you realize you misunderstood something or didn't think of something. And so empirical checking of things is really crucial. You can't just do armchair prediction of everything. And I think they should force the big companies to do experiments on how these things try and get out of control. And I think we already know some of the ways they will. So we'll give them sub-goals, because agents are much more effective at planning your holiday if they can set up sub-goals of sort of getting you there and finding a hotel and stuff. And you don't want to micromanage them, you want them to create the sub-goals. But they will then start creating sub-goals like, if I only had a little bit more control, I could do things better. And that could easily lead to them wanting to take over. I think we need to do experiments on that, because at present it's all just theorizing. Mm-hmm. We don't really have any experience of things more intelligent than us or how to deal with them, or even of things almost as intelligent as us, unless you count Trump. And we didn't deal with that very well. So I think that's one thing government can do. And I think actually Sam Altman agrees on that, that they should be actually doing empirical experiments on how these things try and escape control. Ilya agrees on that too.
It's interesting you mentioned that. So do you think the for-profit versus not-for-profit is part of the issue in terms of the companies or the organizations that are able to develop these kinds of platforms and solutions?
Yeah, so the profit issue is tricky. Obviously, like Google, when it was in the lead in these big chatbots, didn't release big chatbots to the public because it was scared of hurting its reputation by them doing all these confabulations and saying bad things. As soon as OpenAI combined with Microsoft and it went into being, Google had to compete. So the profit motive is going to cause rapid progress, and we're not going to stop that. I mean, it might be rational to say, just stop doing AI now. That might be a rational decision, but it's not going to happen. There's no point even asking for it, because there's no way that's going to happen. And if we stop, the Chinese wouldn't stop. And if the Chinese stop, the Americans wouldn't stop. So I don't think we can ask for it to stop. And we shouldn't ignore the fact that there's many very positive aspects of it, which is why it's going to be developed in medicine and things. We've got to figure out how to try and keep control of it. And I think the profit motive, we saw what happened in OpenAI when everything was stacked in favor of safety, because the company that owned the for-profit bit was a not-for-profit bit which was set up to be concerned primarily with safety. And even in that circumstance, where it was a very unlevel playing field, it was tilted all the way you could tilt it towards safety, and profit won. So that doesn't seem good. And while I'm at it, there's one other thing I want to mention, which is that I think open sourcing the biggest models is completely crazy. My good friend Jan LeCun thinks it's the right thing to do. He thinks we're all going to be fine. We'll keep in control of these things. They won't have any goals of their own. They won't have any desires of their own. I think it's very, very dangerous to open source them. I think it's like open sourcing nuclear weapons. So I think I would love governments to forbid companies to open source big models.
Mindful of time, do we want to?
Yeah, no, we can keep it going.
Okay.
Yep. One question I was talking to you a little bit earlier about was how we go about regulating these things. That the European Union has recently enacted the AI Act, but are there other things we can do to push that stronger? Like would a statutory regulatory profession for computer scientists or for AI architects, would that be something that would strengthen the individual human's ability to fight back against the strong corporate bias that's there at the moment?
Yeah, I should say at this point, I'm a scientist and I develop some scientific things. That doesn't make me a policy expert. So it's very easy to get sucked into making statements about policy when you don't really know much about policy. And it takes lawyers and people who are used to government to understand what the political options are and how you should do regulation. I don't really understand any of that stuff. I don't know about that stuff. A few of my friends have started learning about stuff, like Yoshua Bengio and Stuart Russell have put serious effort into trying to learn about that stuff. I haven't. I figure I'm too old to learn anything new. And so I don't really have much to say that you can trust about any of that.
No, it's an interesting thing. I think that in Ireland, the government has recently appointed an AI council and has a wide representation of academia and industry on it, but not necessarily. There's technical experts, there's industry experts, but isn't necessarily the right advice. And I think that echoes some of what you were saying about the right people to be on these things. Maybe, yeah.
Can I just jump in with one more question? So you mentioned medical applications a couple of answers ago, and I'm interested in where you think some of the low-hanging fruit might be for the applications of AI to medicine in a way that will have great societal benefit.
Well, I think some of the low-hanging fruit is interpreting medical images. I think there'll come a time when we don't need radiologists anymore. Not quite yet. When we don't need them for interpreting medical images, or rather, AI will interpret medical images and radiologists will just check it. But already AI, if you take a fundus image, an image of your retina, AI can see all sorts of things in that image which the ophthalmologist never knew were there and couldn't see. Like you show a fundus image to an ophthalmologist and ask them what sex the person is. They'll say, how would I know from the fundus image? AI will tell you with 80% accuracy. Or you ask them, is this person going to have a heart attack in the next 10 years? And AI will give you a much better bet than an ophthalmologist. So there's going to be a lot of stuff like that where AI can see a lot more in these medical images than doctors can. That's going to be very helpful. But I think, I already asked ChatGPT an awful lot of medical questions because I'm old, and bits, I'm like one of those old cars where bits keep falling off. And it's very good. I don't know how much of what it tells me is nonsense, but it's very helpful.
Well, you live to tell the tale, so that's a good start there. Well, maybe that's a positive note to start looking at the audience for questions. I don't know if we can raise the lights a bit so that we can see.
Yes. Well, there's a trade-off. Either they can see us or we can see them.
We've got some roving mics.
Yeah, I think they need those so the audience can see us.
Maybe there's a few over here.
Are you going to pick the questions?
There we go. That's more like it. That's great. Let's have this gentleman in the check shirt on the right. Okay.
Hi, my name is Amit. I have a question which would be a lot different than anyone would ask today. I'm 30-year-old and I have a job. And I have seen those things, like I started learning through linear regression how mean square error works. Then I saw how to train a network and read about backpropagation that time, and it was pretty interesting and amazing. But with time, I have realized that there are other things in life that you have to do. For example, while I'm seeing a match of, a football match, I'm wasting some of the time that I could spend on learning about transformers, stuff like that. With time, I feel like I don't have enough amount of time to learn and do other things. The question I wanted to ask you is, do you feel that you've compromised a lot of things in life which you could have spent on other things?
Yes.
Do you feel bad about it?
The bits I feel worst about is not spending more time with my children. But if you want to be a good scientist, you have to put your whole self into it. I have a sort of belief, it's just a belief, that you can be good at anything you want to be really good at, but just one thing. So you can be a very good parent, or you can be a very good scientist. But there's a few people maybe can be good at lots of things, but for most people, for ordinary people, you have to really devote yourself to something to be really good at it, and that involves a lot of sacrifices. Sorry. Now, when I was at Google, they were always talking about work-life balance. And my idea of work-life balance is work.
Thanks very much. I'm Brian McNamee from UCD and the SFI Insight Centre for Data Analytics. That was fascinating. I think it's interesting, though, you talked about the move to bigger and bigger models and more computation. Do you see any promising directions that would mitigate against some of the, I guess, the environmental challenges around that and the use of energy around that? Do you see any routes that might be emerging in that regard?
There's sort of two different trends. One trend is you make the model bigger, and without any new scientific insights, if you make it bigger and give it more data, it gets better. And that's bad news in terms of energy consumption. But there's another trend, which is if you've got a big model, you can distill it down to a smaller model, and the smaller model is almost as good. So we can, for serving these big models, maybe we can get better and better at making smaller models. So now there's lots of models that are tiny, where tiny means like 10 billion connections. It's a new definition of tiny, which work almost as well as things with 1 trillion connections. And so maybe, particularly with more scientific insights, we can make them somewhat smaller. But I actually believe that things like GPT-4 knows thousands of times more than a person. And I don't think it can do that. I don't think it can have that much knowledge without having a very large number of connections. So I'm not convinced we can develop models with only a few billion connections that are ever going to be as good as that. So it just looks like bad news to me. More solar panels. Okay.
Hello, hi. Thanks for the presentation. That was excellent. It's a pity Professor Chomsky wasn't here to discuss some of the points you're making, but brilliant. What I wanted to ask you was, ask a computer scientist or a physicist, and they always think that it's imminent that we will have computers that are smarter than us, or we reach that singularity quicker. Ask a neuroscientist, and they're not sure at all whether this is going to happen. We don't understand how the brain works. We're nowhere close to it. So there's these completely different views, and clearly you sit on one side of them, but I wanted your comments on what you thought about the fact that brains evolve, that there are many differences in it. So the question is, common sense is something we think we have and machines do not have yet or are unlikely to have. What are your views on common sense? What does it mean? And also, does language really capture everything? Does language capture enough so that these language models can be smart enough as us? What about all the other things in life?
Okay, so that's a lot of questions. Let me
Apologies.
let me start with. Well, which one should I do first? Let me start with my personal history in this, which is, for a long, long time, I thought that if we made artificial neural nets more like real neural nets, they would get better. And that was the belief that I had until the beginning of 2023. And it was then that I started believing that maybe neural nets using backpropagation on digital computers are already somewhat different from us. So they're similar in the way they hold knowledge as features and interactions between features. But they're different in that you can have many different copies of the same model, and each copy can learn something, and then they can share very efficiently because they all work exactly the same way. And that makes them much better than us at sharing. So they're much higher power than us. They need much more energy, but they're much better at sharing. And I stopped believing that if you make them more like brains, they'll get better. I think we may have reached a point where there's some aspects of brains that you still need to include that we haven't included, like multiple timescales for the weights. So in brains, it's very clear that for the synapses in brains, there are many different timescales at which they get modified. And in neural nets, you just have one timescale. You have a timescale for the activities, so you change the input, the activities change. You have a timescale for the weights, so you change the input, the weights stay the same, and with backpropagation, you change the weights very slightly for each input, and that They change very slowly, and that's learning. But there's no intermediate timescale that corresponds to a sort of short-term memory. So maybe that will help with the artificial neural nets. But basically, I no longer believe you have to make them more like brains. And so it's quite possible that we still won't understand the brain at the point at which these things are smarter than us. And that's what I think now. So my career has been trying to understand the brain and making artificial neural networks in order to try and understand how the brain learns things. And that's been a failure, but there's been some spin-off. Oh, you asked so many questions. That was the first question I answered. The next one, there was a question about, is just language enough, I think. Was that one of the questions? No, but it's amazing how much you can learn from just language. And if you just have language, there's a sense in which it's not grounded. You learn all these relationships between words and how to predict the next word. But in one sense, you don't know what it means. And you have to distinguish between, I think, a model and an interpretation of a model. So you can learn a very good model that's a pretty much correct model of what humans understand without the interpretation that says this thing's a cat. But it would be quite quick to learn the interpretation after you'd learned the model. It's just tying it to reality. If you learn multimodal models, you don't seem to have that problem. So if you do vision as well, you know what a cat looks like. And it's very hard to say, for example, to say, I have a multimodal chatbot. I ask it to draw a picture of a hamster wearing a red hat, and it draws a picture of a hamster wearing a red hat. It's very hard to then say it doesn't understand anything about what this means. It seems to me, if it draws a picture of a hamster wearing a red hat, it understands what that is. Similarly, if you have a robot and you say, open the drawer, and it opens the drawer, that seems very grounded to me. It really does seem to understand. So I actually strongly believe these things understand the same way we do. Even the large language models that don't have this multimodal input, but they understand with less data and better if they do have multimodal input.
Sorry, I had the talk stick, I think, but I'll pass it on afterwards. First of all, thanks very much for an excellent presentation. Throughout history, we've been adapting to technologies, and there's always been resistance, and society comes up with ways at which, things aren't like the past. But then they're accepted. It becomes part and parcel, and people become almost condescending to the past to say that, people were afraid of fire, the combustion engine, the television. Is AI different, though? I involved in a number of AI centers here, and things like ethical AI concerns the adoption of the technology is actually a bigger draw than the development of the technology. If there was complete acceptance, we'd probably be way further down the road. There's this thing that, well, give society enough time, there'll be an acceptance of this technology and adoption. But is this different? Is there an acceptance that we will forever have this resistance and it will never be part of something that, as I said, like the combustion engine or even the internet is it something we just have to accept that this is going to be a problem to be addressed continuously?
My guess is not. My guess is either it'll take over or we'll learn to live with it. I see one future in which it takes over and we're gone, and another future in which we learn to interact with things more intelligent than ourselves and to have a very good symbiosis. So my model for that is, imagine a big company with a dumb CEO, who's probably the son of the previous CEO, with a very intelligent assistant, who's almost certainly female, who's much smarter than he is, and he thinks he's running the company. And in a sense, he is running the company because things he wants get done. But really, the assistant is running the company. Really, the assistant is the one who understands much more than he does about what's really going on. And that would be quite nice for the dumb CEO. So we might all be in the role of dumb CEO with much smarter assistants that make it all work. That's the alternative future. I think we're going to get one of those two futures. But in that second future, we do sort of accept it. And we organize things so that it's to our benefit to live with it. One other comment I wanted to make, you mentioned there was a resistance to television. And I thought, I don't think there was much resistance to television. Retrospectively, I think there should have been much more resistance to television, because look at Trump. He wouldn't be there without television.
Hello. Hi, David Horgan, also a Google alum. So I suppose my question is, you kind of spoke a bit about it in the panel, that AI in the beginning really started with an altruistic kind of research perspective, like what's the art of the possible? And as we've seen, it's developed substantially in the last couple of years. And many companies are moving towards a more closed model. So how are you thinking about striking that balance between really pushing the envelope in terms of innovation, but also having control? Should we be moving towards more of a closed system, more regulation, or does the need and the cost to compute be that limitation in itself? And there should maybe be more controls on the compute power?
So I think I've said that I believe governments should force the big companies who have the resources to put more effort into safety. That's pretty much all I have to say about it. I don't think governments themselves are going to set aside enough resources to investigate these big models. Maybe they should. I mean, maybe the US should be saying, understanding AI and what it can do is we should have something of the same scale as the defense budget. We should have kind of half the defense budget should go on that. And then you're talking about the amounts of money that the big companies, probably more. But I don't think they're going to do that. They've got too many other concerns. And it's not clear they should do that. I think the best role is for try and force the big companies to do more work on safety and try and encourage smart young researchers to work on safety. And there's one thing in particular that needs to be done, which is make it clear to smart young researchers that it won't damage their career to work on safety. Because until quite recently, some people who wanted to work on safety thought, you know, I could work on making the LLM a bit better, or I could work on safety, and I'm going to have a better career if I work on making the LLM better. We need to make good career paths for people who work on safety.
Hello, Geoffrey. My name is Bernadette Benatti. I work at the UCD Foundation, and I thought your speech was terrific. In fact, the whole panel was wonderful tonight. My question is slightly different. In UCD, we do a lot on James Joyce, strangely. And we're very involved in thinking of AI and literature. And I was just wondering about the whole world of aesthetics and what James Joyce would make of AI. And I just wanted to know what advice you would give to people, linguists like myself, about not being worried about AI, about just going for it and see what happens.
I think I'm totally out of my depth.
That's a good enough answer.
I mean, one thing, this isn't James Joyce, but there's something called the Voynich manuscript, which some collector of antiques discovered quite a long time ago. Curiously, Voynich married George Boole's youngest daughter, who was called Ethel Voynich. And the Voynich manuscript has never been interpreted. And I actually got someone who worked for me to try using AI language models to try and understand the Voynich manuscript. There's not enough text there. You'd have to use the images too. There's a lot of images. We never got anywhere with it. I think eventually somebody will. People don't know whether it's a fake. A lot of people have said it's a fake. There's nothing really there. It seems to be a manuscript about strange plants and their properties.
Where can we find out about that? That sounds like a brilliant research project.
Just look up Voynich manuscript.
Okay.
It has some things that suggest that it's genuine. So you know what Zipf's law is, that there's common things and rare things, and they drop off in a particular way. The frequency of them drops off in a particular way. And it obeys Zipf's law. And they didn't know Zipf's law when it was made. So that makes it much less likely that it's a forgery. And already, I haven't followed any of the literature carefully, but I get things in my news feed that say that there's these old very old tablets that AI is now beginning to decipher.
Excellent.
I think there's going to be a lot of that. Maybe it could even decipher Finnegan's Wake.
Exactly. We were just thinking about that one. Thank you.
I'd be interested just in hearing a little bit more about your time at Google, because as I found out about AI, it was really by always using Google to ask questions and get information, and how you see the future of it evolve, and whether it's limited a little bit because NVIDIA seem to have the capacities to get into all the major GPUs, and whether it'll develop commercially throughout.
So what's the question? Will NVIDIA take over from Google?
Yeah, or Microsoft, where it's all going to go commercially.
Well, I have some very good advice for you, which is buy NVIDIA 3 years ago.
I did. Thank you. I'm looking for the next stage.
Okay. Yeah, my daughter got some NVIDIA 3 years ago, and I just persuaded her to sell some of it and buy Intel because it was a bigger upside. And since then, Intel's gone down by 10%. But yeah,
just on this, yeah, fine.
Google will keep existing.
I have great faith in Google still too.
Yes, and Google, a long time ago, people like me were saying, you don't want to see just a bunch of documents that you click on and probably the top one is a good one to click on. You want Google to be able to answer your question by looking at documents, and that's what GPT-4 is now doing. And Gemini's sort of doing that. That's the way it's all going, and I think Google will be in there doing it.
Thank you.
I think we have time for one more question here.
Thank you so much for the interesting evening talk, and it's such an honor to have you here. I'm Fatima from the School of Computer Science in UCD, and I wanted to know, how would you think that AI would change the values in society? Would you think that AI would lead and change values, normative behavior, and cultural change?
I guess I have one thought about that, which is quite scary, which is, before the Industrial Revolution, if you had big, strong muscles and were good at digging ditches, you were valuable. And after the Industrial Revolution, you weren't, because machines could do it better. And it worries me a lot that people of average intelligence and average education are currently valued because there's all sorts of things they can do that are useful. And if AI can just do those things better and cheaper, they won't be valued, and that seems to me terribly dangerous for society. It's a big worry, I think. Sorry.
Maybe we'll take one more question so we don't end on that note.
If you could drive a DeLorean tomorrow and go back in time a bit, who would like to meet? Turing, von Neumann, Hubble and Wiesel, Rosenblatt, and what sort of a chat would you have with them?
I would like to meet Helmholtz. And I'd like to meet Helmholtz believed in unconscious perceptual inference. He basically thought that when you're doing vision, you're doing lots of inference, but it's not kind of conscious, deliberate inference. You're inferring from the proximal stimulus, you're inferring what the state of the world is that gave rise to that. And he was clearly right about that. So that was one branch of Helmholtz's work. A different branch of Helmholtz's work was free energy. There's something called Helmholtz free energy. And what Helmholtz didn't realize was that if you're trying to do inference in a complicated model with complicated latent variables, a statistician would tell you to do inference by, given the current parameters of your model, take the data and figure out the best way for your model to explain the data. And there might be several ways for your model to explain the data, but you have to figure out the probability of each of those ways in which your model could explain the data in order to adjust the parameters of your model. And what variational inference says is, actually you don't have to get that probability right. You can approximate that probability and still guarantee you'll learn a better model, or rather there's some bound that'll improve. And so the two completely different bits of Helmholtz's career, the work on free energy and the work on perceptual inference, were actually very closely related. And free energy is the key to being able to do perceptual inference tractably. And I'd love to tell Helmholtz that.
So, my warmest thanks to Professor Hinton for joining us this evening and for sharing his thoughts on everything from Watergate to Helmholtz to pretty much every other topic in between, including a few stock tips for us all. So I think you'll all agree that it's been an honor to listen to his views. And once again, let's offer our congratulations to Professor Hinton. And thank you for attending.